Hello, class 11th physics, chapter thermal properties of matter. Introduction is done in other video. So here I'm going to discuss first topic, um, and that is thermal expansion. So what is thermal expansion? So when a body is heated, its temperature increases and intermolecular or interatomic separation increases. Due to this interatomic or intermolecular separation increases and body expands geometrically, means in terms of length, in terms of area, in terms of volume. This phenomena is called thermal expansion. Simply expansion means if you provide heat, its thermal state changes, means its temperature increases, and therefore it expands geometrically. So and the converse is also true. If we take out heat from a body, or we can say if we cool down a body, that is its temperature, if its temperature decreases, then it gets contracted also. So there are several phenomena based upon thermal expansion. I'm not going to cover them here, but few of them, like um, jar cap. If it is not opening, we generally heat it so that cap expands and easily be removed. So there are several other examples for that. Sometimes tap jams, so we can heat it and it can be loosen up. So there are several other examples also. Find them, and if you have any doubt in any process which you think, you believe that should be included as mm, thermal expansion, so you can write me in the comments. All right, I will tell you about the mathematical approach for this thermal expansion. Pleased. So linear expansion, expansion of length for related to a wire or a rod. Area expansion related to a surface. Volume expansion for solid, three-dimensional solid. Thermal effect on density. We can't say expansion or any other word. Thermal effect on resistance, thermal effect on resistivity. These are two additional terms, but uh, well, it is not thermal expansion, but the rules will be the same. So that is why I have included them here. Um, these topic has nothing to do with class 11th, but in 12th they are required. So in that way it is important. So let's begin with linear expansion. So let us suppose earlier this was the length of the rod, Li, initial length, and after heating it, this is the length, Lf. So the change in length, delta L, is Lf minus Li. Well, if we decrease the temperature somehow by extracting heat from it, that is cooling it, then what will happen? Then it will get contracted. Still there will be change in length. We will consider change in length. Well, it is observed that this change in length is directly proportional to, oh, I have to write capital L, it will look good. Delta L is directly proportional to initial length and change in temperature. More is the change in temperature, more will be the change in length. And more is the initial length, more is the change in length. That is, if we have a wire pieces of few millimeter, like this much, so it will expand less. And if we have a long wire, it will expand more. So now, if we replace this proportionality with equality, we have to put a constant, and here the constant also resembles with this proportionality sign because it is alpha. Alpha Li delta T, where alpha is coefficient of linear expansion. We will discuss about it later on. All right, so this should be also taken as a complete formula. Now, in place of delta L, we can write Lf minus Li, and that is equal to alpha Li delta T. Take this that side. Lf is equal to Li plus alpha Li delta T. So Lf is equal to Li 1 plus alpha delta T. This is all about change in length. I mean, this one is final length after it gets changed. So if in the numerical, if it is asked find change in length, directly put this, and if find final length, so you need to put this one. Now area expansion. Let us suppose initially this was the surface, area is AI, and later on it has increased because we have supplied some heat to it, so its temperature is increased, so its area increases. And same thing, change in area is directly proportional to initial area and change in temperature. So delta A is equal to, now constant is beta. Sometime still alpha is written there. Anyway, you can choose that also, but you need to put some subscript for that. Alpha for linear, alpha for area, something like that. So that is why I'm using beta. AI delta T, where beta is coefficient of area expansion. So AF minus AI is equal to beta AI delta T, and I am directly doing it. AF equal to AI 1 plus delta, oh, beta delta T. Next, volume expansion. Let us suppose earlier it was this much VI, and now after expansion it is this much VF. So delta V is proportional to Vi delta T, and then delta V is equal to gamma Vi delta T, and here gamma is coefficient of volume expansion. So final, I'm directly writing this. So Vf is equal to Vi, it's looking like T, 1 plus gamma delta T. Now thermal effect on density. How density going to be changed? So we know that density equal to mass upon volume. So initial volume, I'm considering it initial volume. After body is heated, then we don't know what will be the value of rho. So I'm writing this rho I and this rho F. Now see, that will be m upon Vf, and Vf is this. So mass upon Vi 1 plus gamma delta T, and mass upon volume is rho I. So rho F is equal to rho I 1 upon 1 plus gamma delta T. Okay, now see, it is going to be bit mathematical. Rho I 1 plus gamma delta T to the power minus 1. I hope you people are getting it. And this type of expression, when power is either negative or fraction, and side by side this term is very small, so this term is very small, power is negative, so we can expand it by using binomial theorem for first two terms, by binomial theorem for first two terms. So rho f is equal to rho I 1 minus gamma delta t. So this is how we expand binomial theorem, and we have just avoided higher order terms. So from here it is clear that density decreases, volume increases, so density decreases by this law. So now thermal effect of resistance. So once again, change in resistance, I'm directly writing it. So it will be alpha for resistance, and that will be R initial delta T. And from here Rf is equal to Ri 1 plus alpha R delta T. And in the same way, resistivity, and remember this alpha for conductors, it is positive, or for insulators alpha is negative. So if we increase temperature, resistance decreases um, uh, in the insulators. And in the same way resistivity goes. Delta rho is equal to rho I, actually alpha for resistivity, rho I delta T, and rho F equal to rho I 1 plus alpha delta T. So relation between these expansion coefficients. So we will consider the case of a cuboid, a cube, much easier. A cube of side of edge L. So if we heat it, so it gets expanded by this amount. Its length now become L plus delta L. So this is initial length L, now this is final length L plus delta L. So we'll begin with that expression. We know that LF is equal to Li 1 plus alpha delta T. Alright, to avoid confusion, let's write this LF and this as Li, Li, Li. So that's all for first step. Now second step, let's see about its surface. Its surface earlier this and now has become this one. So AF is equal to AI 1 plus beta delta T. Okay, so how this surface, we can find the area of this surface. We know Li, Li, and this is LF, LF. So here we can say that AI is Li square, because it's a square, so side into side. And similarly, AF can also be given as LF square, this final length square of that. As we know area of a square, though simply it is that. So we can put these two values here. Therefore, L square F is equal to Li square and 1 plus beta delta T. Other than that, one more thing we can do. From here, we can put the value. I'm writing it equation 1. So LF is this one. Oh, somewhere we have to use similar symbols, so I'm making them small letters. So now LF is this much, so I am putting this value here, so it will become Li 1 plus alpha delta T squared. So what is the meaning of that? LF, what is LF? This thing is LF, so we have squared that, equal to Li square 1 plus beta delta T. Now Li square 1 plus alpha delta T square equal to Li square 1 plus beta delta T. L square will get cancelled and we will take whole square of this. So this is 1 will get cancelled. And see one more thing, this alpha is already has very small value. The order of this alpha is about 10 to the power minus 5, so its square will go vanishingly small. So alpha square can be neglected. Now 1 get cancelled, alpha square is neglected, so this much has left over there. So we can say that 2 alpha is equal to beta. Now let us suppose for volume Vf is equal to Vi 1 plus gamma delta T. And what is Vf? It is Lf cube, which is equal to Li cube 1 plus gamma delta T. And once again, value of Lf is this, Li 1 plus alpha delta T cube, Li cube 1 plus gamma delta T. So this is Li cube 1 plus alpha delta T cube equal to Li cube 1 plus gamma delta t, li will get cancelled. 1 plus alpha delta t whole cube is equal to 1 plus gamma delta t. Take cube of it, so a cube plus b cube plus 3ab square. 3a is 1, b square is equal to plus 1 plus gamma delta t. So now 1 will get cancelled. Alpha cube term here also, alpha square term, entire term will vanish. So alpha cube term and alpha square term can be neglected. Alright, so oh my god, one thing I missed. 3a square b plus, I'm writing it here, plus 3a square b. So 1 and b is alpha delta t. Otherwise, there was nothing to work with. Alpha delta t equal to gamma delta t. That is 3 alpha equal to gamma. From here, we can say that if we find alpha ratio beta ratio gamma, we can find 1 is to, for beta it is 2 alpha, 2 is to, for gamma it is 3 alpha, 3. That's all. So here we have a question so that we can understand this concept well. A girder is a very thick metal beam. It looks like this. Alright, used in railway track is 10-meter long, so it is initial length 10 meter. At 25 degrees Celsius initial temperature in the hot summer, okay, so at 25 degrees Celsius it is 10 meter long. If in the hot summer temperature increases to 45, now see, one interesting fact is there. I'm directly finding delta t. I'm using capital T, which is related to Kelvin scale only. Actually, we used to write temperature with capital T alphabet if temperature is in absolute scale, that is Kelvin scale. And to change Celsius into Kelvin, we have to add 273, to be very precise, 0.15 into that Celsius temperature. But remember one thing, delta T in Kelvin is equal to delta T in Celsius. Their difference is same. And why is it so? You can see T initial is 25, T final is 45. So delta T, this small letter for Celsius, will be 45 minus 25, that is 20 degree Celsius. Now if we convert it into Kelvin, 298 by adding 273, I am avoiding 1.15, and TF, it is F actually, is 218. So if we subtract both of them, delta T, still the answer will be 20 Kelvin. So remember this thing. So I am not going for this entire calculation. Remember this thing. We have to directly put 45 minus 25, that is 20 Kelvin. Here it is the case of length increase in length, but coefficient of volume expansion is given here. So from this formula we can say, oh, gamma equal to 3 alpha. So here if alpha is required, then it will become gamma by 3. By 3 per Kelvin. So it will be 1.2 into 10 to the power minus 5 per Kelvin. And now what? Find increase in length. Actually delta L is required. So delta L is equal to, we know it is alpha Li delta T. Alpha is 1.2 into 10 to the power minus 5. Li is 10 meter and delta T is 20. Two zeros adjusted here, so it will be 2.4 into 10 to the power minus 3 meter. It is nearly 2 mm, 2 millimeter, which is quite acceptable answer. So, are these formulae applicable everywhere, or is there any limitation, any restriction while applying these formulae? So, generally, these are applicable for each material. But, like if we take the case of water or silver iodide, then this volume expansion and effect on density will change. So, for water, a very, very special concept comes, which is called Enemless expansion of water. So, what is anomalous expansion of water? So, when water is heated from 0 degree Celsius to 4 degree Celsius, it contracts instead of expanding. It gets contracted, and this is called anomalous expansion of water. This is called this entire thing, anomalous expansion of water. So, we can show it graphically, and this is the graph. Let us suppose uh, we have taken, let us suppose, 1 kg water, or 1 gram, that will be fine. We know that density of water is 1 gram per centimeter cube at 4 degrees Celsius. So that is why I have taken, because due to expansion its volume will change, either increasing way or decreasing way, but its mass will remain same. So we have taken 1 gram of water. So what happens actually at 4 degrees Celsius, we will find its volume, this side volume and this side temperature. So at 4 degrees Celsius, right now I'm writing it with small t because I'm using it in Celsius, and I will put a subscript C also here. So this is 4 degrees Celsius, of course. So at 4 degrees Celsius, according to this value of density, we can say its volume will become 1 centimeter cube. See, density 1 gram per centimeter cube means 1 gram will be occupied in 1 centimeter cube volume. So at 4 degrees Celsius, volume of water, 1 gram water will be 1 centimeter cube. Now what will happen? If we increase temperature, it expands. Not linearly, but of course it expands. So if we decrease temperature, it don't go downward. Instead, it show this kind of graph. So from 0 to 4 degrees Celsius, water gets contracted, and later it start its volume increasing. If we draw the same diagram for density with temperature, so we know that at 4 degrees Celsius, density of water is maximum. Below that, it is lesser. Above that, it is lesser. What is the reason for that as anomalous expansion of water? So there are several theories. Most appropriate theory is hydrogen bonding and trapping of air in those pockets. So when water is heated, so when temperature increases, those pockets breaks, and that is why it start contracting. But up to a certain limit, it start expanding, because when it stabilize itself, then after that it start in expanding, intermolecular spacing increases. But before that, there is a shape. Actually, the shape of ice turns into water. Still, there are some hydrogen bonding in a very different manner, and when those bonds break, after that, um, it start contracting because those vacancies are filled up by the uh, other molecules of water. But after at 4 degrees Celsius, beyond it start getting contracted, and instead they start expanding. So this is called anomalous expansion of water, but this is very useful for survival of aquatic animals. And also it is believed that uh, if this property have would not be there, then in ice age entire all the oceans would be frozen up. But it didn't happen. It is because if this is a lake, then how will its cooling goes? So this is the surface, and if this temperature is decreasing, let us suppose 6, then 5, then 4, when its temperature becomes 4, then density of this layer becomes maximum. So if it has maximum density, so we know that the material which has more density sinks. So this water will sink into that water which is not at 4 degrees Celsius, which is bit above it. Let us suppose 5 degrees Celsius. Now this water will settle down here, this water will take its place, and again it will a convection current will go like this. This layer becomes 4 degrees Celsius, sinks, lower level rises up. Again, same thing happen. It goes on repeating till entire all water contained by that water body becomes 4 degrees Celsius. Now, if it is further cooled, then we know that now whatever be the water, how much the water is there, it will have density less than the density of water at 4 degrees Celsius. So if it is getting cooled now, then it will start getting frozen from top to bottom, from here to here. It will goes on decreasing. Other than that, ice is itself an insulator of bad conductor of heat. So now no more cooling. It will get cool, but not with that amount. So this is how aquatic animal can survive in this 4 degree Celsius temperature. So next concept is thermal stress. Mostly it is included for competitive level, but for your own interest you can study it. So let us consider a situation where we have a wire and we have stretched it, and then thermally we are um, making it to get contracted. Okay, or in other case what we can do, this was the wire, and not the wire, a rod, a rigid rod, and we have clamped it from both the sides. And if now what we are doing, we are increasing its temperature, so it will try to expand, but it's we have just rigidly held it, so there will be a stress produced in it. That is, to retain its shape, we are applying some external force that will create a stress. So that will called thermal stress. Okay, so let's begin. We know that delta L is equal to alpha Li delta T, thermally expanded rod. So next thing is delta L by Li equal to alpha delta T. It is a change in length upon original length. So I'm putting it as equation 1. Now, alright, if here a stress F upon A was coming into influence, or if here we are applying some additional force and that is producing this kind of stress, then we know that y equal to stress upon strain, where y is Young modulus. So y equal to stress, I'm writing it stress only. In fact, I'm writing it thermal stress upon strain, delta L upon Li, which is alpha delta T. So y equal to thermal stress upon alpha delta T. So thermal stress equal to Young modulus temperature coefficient of linear expansion delta T. This will be the thermal stress. So to end this lecture, let me tell you about the unit of alpha, beta and gamma. We know that their unit is per Celsius, per degree Celsius, or per Kelvin for all of them. But why? So if we make formula for alpha, so that will be equal to delta L upon Li delta T. If we put the units of all of them, meter upon meter Kelvin, so it is Kelvin inverse. Or if it is measured in Celsius, then Celsius inverse. If we take the formula for beta, so it will look like this. Once again, meter square by meter square Kelvin. So finally it is Kelvin inverse. And in the same way for gamma, you can try it of your own. That's all in this video. Bye bye.